Hey guys, today I'm going to go through a bunch of these questions. A couple of them that I think are tricky or might throw you with little things. I'm also not going to go straight to the final answer. If you want the final answer, it's in the solutions, which are in the Google Classroom. I'll just set things up for you and talk you through it. So let's get started with number one. I just wanted to do this one quick recall for what an alpha particle is, and just this sort of mass spectrometer idea once it's in that perpendicular magnetic field. So first thing we got to do is we got to do our situation. In this case, it's kind of like F net cos equals F net circle. And our cos is the magnetic field, and the formula for that is BQV. And our formula that we want to use in this case, since we're interested in speed, is mv squared over r. Now we're interested in the speed, so we're going to solve for that. We'll cancel out one of our v's, rearrange to solve for v, and we will end up with our velocity equals BQR all over M. So then we just plug stuff in. So we have our magnetic field. Remember, it's measured in Teslas, or magnetic field strength, times 10 to the minus 1. I should have just done 0.422. And then our charge, this is the tricky part, it's an alpha particle. So remember, that's a helium nucleus. It's got 2 protons, 2 neutrons. So it's the charge of 2 protons. So it's Q is 2 times 1.6 times 10 to the negative 19. Remember, that's your elementary charge. And then our radius is given to us. It's 1.5 times 10 to the minus 3 meters. Remember, we got to work in meters. Some of the other questions throw centimeters at you, so you got to convert them. And then we will divide by the mass, which is basically 4 times the mass of a proton. Or you could do 2 times the mass of the proton plus 2 times the mass of the neutron, but it's about the same. I'm just going to do 4 times the mass of the proton. Mass of the proton, I believe, being 1.67 times 10 to the negative 27. Throw that in, you should be good. Kind of makes sense. BQ, because we got 2 protons, 0 electrons, our radius, and then our mass is 4 times the mass of a proton, or more accurately, 2 times the mass of a proton plus 2 times the mass of a neutron. All right, let's move on to the next guy. Number 3 here I picked because it mentioned charge to mass ratio, which you're probably not as used to solving for. Again, we've got this whole like magnetic or mass spectrometer kind of thing, like after it enters the uniform magnetic field, and we find the radius. So in this case, let's set it up. We've got same things before, F net cos equals F net circle. Our formula is exactly the same. We got our BQV equals mv squared over r. We can cancel out one of our v's. And then what we want is Q over M, because that is our charge to mass ratio. So if we rearrange everything, we've got Q over M on one side. This is one thing. This is our charge to mass ratio. And that's going to equal V over BR. BQR? No. V over BR. Make sure I'm not leading you astray, and looks good. Okay, then we just plug it in. We've got our velocity, 3.6 times 10 to the 5. We've got our magnetic field strength, 6.1 times 10 to the minus 1. And we've got our radius, 7.4 times 10 to the minus 2. Plug that in, you're done. That's it. All right, next guy. You've got alpha particles again. undeflected through magnetic and electric fields that are perpendicular to each other. That sounds like the velocity selector part of the mass spectrometer to me. So let's give it a shot. So we got their speed, and we are looking for the strength of the electric field. So let's set it up again. In this case, our magnetic field is equal and opposite to our electric field because they were undeflected. So your magnetic force has to be equal and opposite to your electric force. So we put in their formulas, EQV equals EQ, and notice our Q's cancel. And then we want to solve for strength of the electric field, so it's really just the magnetic field strength times the velocity. This is a V, not an R. So we just do 2.2 times 10 to the minus 1, or 0.22, Teslas times 7.8 times 10 to the 5. That's going to equal your electric field strength. And that's it. On to the next guy. 4-7 here. You've got these electrons accelerated from rest from a potential difference of 2.5 times 10 to the 3 volts. I'll write it out just because it's a little confusing with this. You would actually start at 0 volts and go to, or potentially, why don't we, depends how we want to do this. I'll just write out how it has to be. So it'll be going from 0 volts to 2.5 times 10 to the 3 volts. And so we can just do it as a before equals after. I could also have done this with a change in energy equals change in voltage times charge. That would also work. So basically it's going to lose a ton of potential energy, and all that's going to become kinetic. So it's just energy before equals after. So before we've got 0 potential energy because it's 0 volts, and our charge is, or our VQ is our potential energy. And it's at rest right here. So here's where it starts. It's got 0 potential energy and 0 kinetic. And afterwards, it's got a pile of negative potential energy. So it would be VQ again, and plus 1/2 mv squared. So that would be, your voltage is 2.5 times 10 to the 3, and your charge is negative 1.6 times 10 to the negative 19. So that gives a bunch of negative potential energy, and then to cancel that out, we're going to need a pile of positive kinetic. So whatever the mass of the electron is, I think it's like 9.11 times 10 to the negative 31 or something, but not 100% sure. So I'll just write this in. You can look it up in your data pages. If you don't have your data pages, just go to My School, and in My School, under exam prep, you've got links to all the old exams. The only I got your formula sheet just by copying one of the formula sheets attached to one of the exams. June 2000 to be exact, if you want the exact one, but any of them will do. All right, next one I wanted to go over is number 11. So we got a negatively charged particle with mass 8.4 times 10 to the minus 7. It's traveling at a velocity of 5.6 times 10 to the 5, perpendicularly through a magnetic field. So we got another mass spectrometer style thing. The new twist on this guy is this excess electron. So we're going to have another step at the end. We'll solve for charge, and then we also have this centimeters thing, so we'll have to convert that to meters. But aside from that, we start at the same and just solve for charge. So F net cos equals F net circle. Our cos is BQV. We'll use mv squared over r because we have our velocity. It's usually that one. Cancel out one of our v's. And we want to solve for q. So we will say our charge is equal to mv over br. And then we solve for that, being careful to convert this guy to meters. So we've got our 8.4 times 10 to the minus 27 times 5.6 times 10 to the 5 all over our magnetic field strength, which is 2.8 times 10 to the minus 1, and our radius, which we convert to meters, which would be, you got 3.5 centimeters, that's the same as 0.035 meters. Plug all that in, you will get a charge in coulombs. We don't want a charge in coulombs. We want number of excess electrons. And so we would want to divide by the elementary charge. So our last step is number of excess electrons. By the way, you might want to, this thing here, because it doesn't take into account which way the electrons were deflected, Q will always be positive here, just because of how we have it set up. So you might want to make it negative to be exact in this case. Anyway, so your number of excess electrons is going to equal your charge you get out of that, divided by your elementary charge, which is 1.6 times 10 to the negative 19, or make it negative if you've made your charge negative. And then you're done. It's just this little extra step that's different. All right. Is that all I wanted? That's all I wanted. Thanks for listening. If you made it through this, congratulations. You win a prize.